So this table is reference to hydrogen. So the half cell reaction of hydrogen is 0. These are all presented as reduction reactions, right? Or something, some element plus electrons becoming of the reduced state of that element. It's same, all plus electron reactions, reduction reaction. So the more positive that value is, so the more willing that reaction is to take place, or the more willing that element to take the electrons, or the more negative that element the half cell reaction is, then the more willing it is to give out its electron, or the more stable the backward reaction is. Let's take the example of copper and zinc. So if you monitor react copper and zinc, so you look at the table that copper reduction half cell reaction has a value of positive 0.34 and zinc has a value of minus 0.76, which means that comparing copper and zinc, so zinc is ready to give its electron to reduce copper ions, and therefore copper ions will be converted into copper metal. Okay, so let's take this case. So case 1, where you have a container filled with electrolyte that has copper 2+ ions in it, and then okay, so if you put in zinc rod or zinc metal into it, so what will happen here is that zinc metal will immediately give its electron away to copper 2+, right? Because zinc is more negative than copper, so in this situation copper 2+ will be willing to take the electrons from zinc 2+, and zinc 2+ is more willing to give its electron. So over time you will have the zinc will dissolve, the zinc will dissolve, and you will have here copper metal, and then you will have zinc 2+. This because if you again, if you dip zinc metal into a copper 2+ containing solution or electrolyte, so the zinc will give its electron away to copper 2+, and the copper 2+ will be converted into copper. Why? Because the standard reduction half cell reaction for copper is more positive than zinc, right? It's at the top position, higher position than zinc. So zinc will give its electron to copper 2+, and copper 2+ then as a consequence will be reduced into copper metal. Alright, okay, so what happened then if you have, let's flip the situation, that you have copper metal and you dip it into a solution containing zinc 2+, right? So in the first case you have zinc metal dipped into an electrolyte containing copper 2+. In the first case, let's say case 1, you have the zinc will give its electron to reduce copper 2+, forming copper metal. So for case 2, where you have copper metal in a zinc zinc 2+ containing solution, so what will happen? Well, nothing will happen, right? Because copper is already very stable. The copper has a more positive value than the zinc. It cannot reduce zinc 2+, because between copper and zinc, copper is more stable in a metallic state, and zinc is more stable in the oxidized state or ionic state, copper 2+. Okay, so nothing will happen. Great. So if I wanted to build a battery cell from copper system and zinc system, so copper system will be the cathode because it is more positive, so it's more ready to take electrons, and anode, and zinc will be the anode. All right. So if I say what is the anode, anode would be zinc metal oxidized into zinc 2 plus 2 electron. All right. This has a potential, standard potential of minus 0.76 volt, and the cathode would be the reaction taking place on the cathode would be copper 2 plus ions reduced into copper metal, and this has half cell reaction potential of 0.34 volt. Now if you notice that I'm writing the half cell potential exactly from the table, right? Exactly from the table, 3.76 minus 0.76. But the way I write the anode, because the anode is going through oxidation, so I have to flip it. Okay, I have to flip the half cell reaction. So this is presented as reduction, but because we want to build a cell, electrochemical cell, so I have to flip the anode. I have to flip the zinc reaction so that the zinc is giving out electrons, right? We know that zinc will be ready to give electrons because the value of the potential is more negative, and because the cathode reaction is copper, so we keep it as it is from the table. So the net reaction here would be zinc metal plus copper 2 plus going to the forward reaction, forming zinc 2 plus and copper metal. All right. So as in the first case, if you have zinc metal, you have copper solution, and the electron on the interface here on the surface of zinc will give out its electron to copper 2 plus, right? So the electron is just moving in on the surface of zinc, going to and attacking the ions to form copper metal. But sorry, you will not get anything from that, meaning that you cannot utilize the electric potential energy of the electrons to do work, meaning that to light a bulb or to do anything that your battery do for you normally. So in order to utilize the energy of the electron, so you wanted to separate this reaction, right? So how do you separate it? Then you form a separate cell. Okay, one for the anode. This has zinc metal. This has zinc ions in the electrolyte, and here you have copper. And then you connect this to a voltmeter to read the volt, or to a light bulb, and you need to have a salt bridge. Alright, give that a little bit of shading. Right, so this is the anode as a negative electrode, and this is the cathode, positive electrode. Okay, so what is the potential, the E of this cell, right? Because we are using standard half cell reaction, so the E cell will also be a standard of the E cell. This is calculated with the formula E of the cathode minus E of the anode. Now, what do we use for the cathode? It is the copper half cell reactions. So this is not standard condition. It's 0.34 volt minus what is the E of the anode? the E of the anode is from the table minus 0.76 volt. So this will give you around 1.1 volt, positive 1.1. So positive means that this reaction is spontaneous. Zinc will give its electron through the cable, in this case, right? So it has to go to the cable, and if you have a light bulb or some electronic device to do work, then the electrons can go through that circuit and to do work, and then reduces copper 2 plus here, right? Now in the anode side, because you are oxidizing the zinc, you will produce more zinc 2 plus, right? More zinc 2 plus ions. And on the cathode side, you will get less copper 2 plus because you're reducing it. So what will happen? You will have a charge imbalance. You will have more positive charge here and less positive charge here. So this is the job of the salt bridge, to neutralize that. Okay, to neutralize the excess positive charge and excess negative charge here. Okay.